Madam, madam, start the class, madam.
Okay, sir. Good afternoon, one and all. In last class, we discussed about the properties of transition elements. Those are atomic and ionic sizes, and ionization enthalpies, and oxidation states of transition metals, and how to calculate the magnetic properties. In last class, we discussed how to calculate the magnetic moment given ion. So I will give one trick to is remembered. If n values is equal to 1, then mu value is equal to 1.something backgrounds. If the n is equal to 1, then n is equal to number of unpaired electrons. If you have n is equal to 1, then weight value 1.73 Bohr electrons. So you easily remind the number. Okay? If the n is equal to 2, then you easily remember just 2. If n is equal to 3, then value is we get the 3. Yeah, if the n is equal to 4, then we get 4. N is equal to 5, then we get 5. These are remembered easily. Next, transition metals forms colored compounds also. How these forms the colors. Okay. When visible light falls on transition metal compound or ion, if any one of the electrons present in given ion or compound in this lower energy orbital, then it gets the promoted to higher energy d orbitals. This process is called d transition. Here, where these electrons get promoted from the lower energy to higher energy level, this is taken by absorption of visible light. When an electron from lower energy d orbital is excited to a higher energy d orbital, the energy of excitation corresponds to the frequency of light absorbed. The frequency is generally light visible region. The color observed corresponds to the complementary color of light absorbed. The frequency light observed is determined by the nature of ligand. How these forms colored compounds? They form colored ions due to presence of incompletely filled d orbitals, and any unpaired electrons are present in this given compound, then they exhibit the colors. They can undergo d transition by absorbing color from visible region and radiating complementary colors. Then, very often those of D0 and D10 metal ions, and these are not forming colored compounds. The D0 and D10 configuration of compound do not show the color compounds. Because of in the electron transition of DD electron within D subshell, these are known as DD transition. Here D0 and D10 metal ions do not show the type of transition. Then here the electrons sorry.
Madam, Priya ma'am.
Priya ma'am. Priya ma'am. Is there any technical problem, ma'am, on your end?
Hello, madam.
Hello. Is there any technical problem on Swapna ma'am's end, ma'am?
Yes, she's again signing in. I mean, she's again joining.
Okay, ma'am.
Minutes,
Okay.
2 minutes.
Okay, ma'am.
Sir, make her host, sir. Okay, madam. Okay.
Continue, madam.
Example, aqueous Cu plus 2 ions are blue in color, whereas aqueous Zn plus 2 ions are colorless. Because of here, the Cu plus 2 electronic configuration is D9 and 4 is 0. In this 3D9, that means it has one unpaired electron, so the colors. But Zn2, it has completely filled 3 shell. It means 3D, so that it does not exhibit colors. Not only Zn plus 2 and CD plus 2 also are fulfilled. Then Ti plus 4, all d orbitals are vacant. So no d transition occurs. They do not absorb radiation, so they are colorless. Difference between Cu plus and Cu plus 2 ions. Cu plus is colorless. Cu plus 2 is green color. Because of in Cu plus it has D10 configuration, and Cu plus 2 it has D9 configuration. Because of the copper lost 2 electrons from the 4s1 and 3d orbital. So it has one paired electrons. That is the reason Cu plus 2 is blue color, and Cu plus has completely filled the orbital, so it is colorless. So these are the color of the corresponding ions in with unpaired electrons are corresponding. Next goes to the catalytic properties. Transition metals and some of their compounds generally used as catalysts. These transition elements in some reaction forms unstable intermediate compounds, and in other cases they provide suitable surface area where gases are absorbed. Nickel is used, for example, nickel is used for hydrogenation of vegetable oils, and iron is used in manufacture of ammonia. And nickel platinums are very heterogeneous catalysts, and platinum, plutonium, and palladiums are used in catalytic converters. V2O5 is used in conversion of SO2 to SO3. They can form the interstitial compounds also. The transition elements forms the interstitial compounds. What are the interstitial compounds? The transition metals form compounds of indefinite structure and proportions, which are called interstitial non-stoichiometric compounds. The reason is variable oxidation states and defects in their solid structures. The transition elements form a large number of interstitial compounds in which small atoms such as hydrogen, carbon, boron, and nitrogen occupy the empty space in their lattice. They are usually non-stoichiometric and are neither typically ionic or covalent. These are some examples too for the interstitial compounds. And they can form alloys. The transition metals are mixed with other metals or non-metals to form alloys. Example, steel. Steel is an alloy of iron and other elements such as carbon, nickel, manganese, and chromium. And one more example is bronze. It is a combination of copper and tin. And next goes to gold. Then gold is an alloy and it is a combination of copper and silver and gold. Next to brass. Brass is a combination of copper and zinc and cast iron. It is a combination of iron and carbon. And sterling silver. It is a combination of silver and copper. These alloys are two types, and formation alloys are two types. One is substitutional alloys and interstitial alloys. Substitutional alloys. Atoms of one metal are substituted by atom of another metal forms the substitutional alloy. But in this different metal occupies, these are different. The different metals occupies interstitial space. These are interstitial space. That means holes. Interstitial space is nothing but holes in lattice structure. The interstitial alloys formed by different metals occupies interstitial space in lattice structures. Next, they can form complex compounds. The transition metal forms the complex compounds. A complex is formed by a central metal atom or ion is surrounded by other molecules or ions which forms daily covalent bonds with the central metal atom or ion. What are the complex compounds? A complex is formed when a central metal atom or ion is surrounded by other molecules or ions which forms daily covalent bonds with central metal atom or ion is called complex compound. The transition metal forms a large number of complex compounds. These are examples of complex compounds. FeCN6 3 minus, FeCN6 4 minus, and some more examples of complex compounds. Then some important compounds of transition elements. The K2Cr2O7 and KNO4. K2Cr2O7. It is ionic compound and orange red color. It is a good oxidant. Then how to prepare K2Cr2O7? It is prepared from ore. Chromite ore is nothing but FeOCr2. Then this chromite ore is react with Na2 in presence of oxygen, which is heated with Na2 presence of oxygen. It is nothing but roasting. Okay, to forms the sodium chromate, that is NaO4. It is a colored compound. Then in its acidic medium, means addition of acid, the sodium chromate is converted into sodium dichromate, that is Na2Cr2O7. It is easily soluble in water. It is react with KCl. Whenever it is react with KCl, the potassium active than the sodium. Then this potassium is replaced the sodium from the sodium dichromate to form Cr2O7. It is orange color. This is the preparation of Cr2O7. And Na2Cr here. Na2CrO4, it is formed in this here. This is the Na2CrO4. This is sodium chromate is undergoes to dissociate to Na plus ions and CrO4 minus 2 ions. It is called chromate ion. It is in yellow color. Then it is in acid medium. It forms the dichromate ion. Then chromate ion is in acidic medium, forms the dichromate ion. It is orange color. Okay. Then here chromate ion is yellow color. It is in acidic medium, convert to dichromate ion. This dichromate ion is orange color and it is in basic medium. It is in basic medium and it is converted to chromate ion. Okay. Acidic medium, chromate ion is converted to dichromate ion. In basic medium, dichromate ion is converted to chromate ion. So in acidic medium, which is more stable? In acidic medium, dichromate ion is more stable. In basic medium, ion is more stable. Okay. In acidic medium, dichromate ion is more stable. In basic medium, chromate ion is more stable. So that means here potassium dichromate dissociate to form 2 plus ions and dichromate ions. The reaction of potassium dichromate H2O7 is reacted with cold H2SO4 to form the CrO3, that is chromic anhydride. If it is react with the hot H2SO4 to form the Cr2SO4 and release the oxygen. This Cr2SO4 is known as chromic sulfur. When it is dissociated, forms the 2Cr plus 3SO4 minus 2. Means finally potassium dichromate, that is K2Cr47 in acid medium to form the Cr plus 3 ions. Here K2Cr2O7 undergoes dissociate to potassium ions and dichromate ion. It is the structure of dichromate ion. In this dichromate ion, these electrons involves in delocalization. Because of this resonance, all the CRO bond lengths are same in the dichromate ion. Related to this dichromate structure, how many CRO bonds are same in dichromate ion? This is the previous most important question in competitive purpose. Due to resonance, 6 CRO bond lengths are same. Due to the resonance, 6 CRO bond in chromate ion. K2Cr2O7, it is strong oxidizing agent because of in this K2Cr2O7, if you calculate the oxidation state of this chromium, then we will get +6. And same as well, generally in this chromium, its atomic number is 24. Its general electronic outermost electronic configuration is 3d541. Here the chromium lost 6 electrons. So it exits the maximum oxidation state is nothing but a highest oxidation state, that is +6, because it lost 6 electrons, then it gets the +6 maximum oxidation state, and further it cannot lose electrons, so it cannot undergo oxidation due to it not get more than +6 oxidation state. Because of loss 6 electrons, it has stable configuration, that is equal to argon electronic configuration. So it not loss more than 6 electrons, so it cannot undergo oxidation, but it undergo reduction. So KCr positive dissociative for the potassium ions and Cr2 ions. It is supposed to give the Cr+3 ions. Now to balance the Cr2O7 minus and Cr+3. Then in Cr2O7 minus, this side 2 chromiums are present. This side only 1 chromium is present. So now you add 2 for Cr+3 ions. Next you balance the oxygens. Next step you balance the oxygens. Here this side Cr2O7 minus 2, 7 oxygens are there. But this side only there is no oxygen. So to balance the oxygens, water molecule is added. So next step, this side 7 oxygens are present, this side no oxygen present. So this side you add 7 water molecules. Next step, you balance the hydrogens. To balance the hydrogens, in acidic medium H plus ions is added. In this here 14 hydrogens are present this side, but this side no hydrogen are present. So you will add 14 H ions this side. Next you balance the electrons. So here -2 electrons, -2 is present. Here 14 H is present. Okay. Then for the 14, 2 is less, we get the 12 plus charges. But this side only 6 charges are present. Okay. To balance the electrons, add 6 electrons to this side. So we will get the balance equation, that is Cr2O7 minus 2 and 14H plus and 6 electrons, the 2Cr+3 and 7H2O. Here K2Cr2O7 itself undergo reduction. That means it makes other element undergoes to oxidation. So it is a strong oxidizing agent. That means it oxidizes these ions, I-2, I2, Cl minus 2, Cl minus 2, Cl, and F plus 2, Fe+3. I meaning you remember, these are most important for the competitive purpose. Then how to these oxidize? For example, if it is oxidize the Sn to S plus 4, what the reaction we get? Okay, first of all, you take this Cr2O1 minus 14H plus and 6 electron gives 2 Cr3 and water molecules. Then how this is oxidized the Sn plus 3 to Sn plus 4. Okay, before adding half reaction to half reaction, first balance this N plus 2 to Sn plus 4. This balance the electrons. This side has plus 2 charge and this side has plus 4 charge. To balance these charges, to add 2 electrons this side. Okay, then Sn plus 2, Sn plus 4 reaction has only 2 electrons, but in 6 electrons are present. To balance these two half reactions, then it is Sn to those S plus 4 plus 2 electrons is multiply with 3. Multiply with 3, we get the 3 Sn plus 2 and 3 Sn plus 4 and 6 electrons. Now it is at to this half reaction. Then overall reaction got Cr2O7 minus 2 and plus 3 Sn plus 2 and plus 14H plus ions, that gives Cr plus 3 and plus 3 Sn plus 4 and 7 water molecules. Then reaction with H2O2. Potassium dichromate is react with H2SO4 and H2O2. They get the chromic peroxide. This chromic peroxide structure is this one, butterfly structure. Next goes this potassium dichromate is used in the chromyl chloride test. How to find this? How to do this chromyl chloride test? When potassium dichromate is treated with strong sulfuric acid and a chloride to form the reddish brown vapors of chloride are formed. This is the chromyl chloride. Whenever the potassium dichromate and added with H2SO4 and potassium chloride, reddish brown vapors are evolved. These reddish brown vapors are chromyl chloride. This is CrO2Cl2. This is called chromyl chloride. This test is used in detection of chloride ions in qualitative analysis. The formation of reddish brown vapors, that is called chromyl chloride, confirms that particular salt is having chloride ions. This is called chromyl chloride test. Okay, the potassium chrome is used for the detection of chloride ions in any given compound. Next goes to KMnO4. Okay, this KMnO4 also not undergoes to oxidation, then itself undergoes to reduction. KMnO4, the manganese, actually the manganese is the electronic configuration is 4s2 and 3 5. The KMnO4 in the KMnO4, the manganese oxygen state is placed. Then in acidic medium it forms the MnS2. In basic or neutral medium it forms MnO2, and in strong alkaline medium it forms K2MnO4. The KMnO4 itself undergoes reduction, means it makes other element undergoes to oxidation, so that it is a strong oxidizing agent. That means this makes the other elements undergoes to oxidation. In acidic medium, it oxidizes the FAS2 F plus, NO2 minus to NO minus, and I minus to I2, H2SO and I minus to O3 minus, S2O3 minus to SO4 minus 2. Next goes to F block elements. These are also called inner transition elements. F block elements. What are the F block elements? In the differentiating electron enters into anti-penultimate shell, that is N minus 2 into F subshell, are called F block elements. F block elements means in which the differentiate electron enters into anti-penultimate shell. What is the anti-penultimate shell? N minus 2 into F. Here N minus 2 is transfer anti-penultimate. These are all F block elements. F block elements placed at the bottom of the periodic table. These are the F block elements. These are the F block elements. General electron configuration is N minus 2 into 1 to 14 and N minus 1 D 0 to 1 NS2, whereas N is equal to 6 or 7. These are so called inner transition elements. Why they are called inner transition elements? Because the elements which are partial filled anti-penultimate shell are called inner transition elements. It has two series of elements. Those are Lanthanide series. These are also F block elements. And next goes to 4F block elements and 5F block elements. These are called actinide series. It has two series of elements. The 4F block elements. These are also Lanthanide series, and 5F block elements. These are also called actinide series. The 4F and 5F series actually placed in sixth and seventh p of third groups. Okay, the 4f and 5f series are these are the 4f series, and next goes to 5 series. These are placed at the 4f series is placed at the sixth period, and 5f series is placed at the seventh period and belongs to third B group. Reason for this is similarity in chemical properties. Reason for this is similarity in chemical property of elements from the lanthanum to lutetium and from actinium to lanthanum. 4f series elements. These are all called lanthanides. These are started from the cerium and ends with the lutetium. The 4f elements are started from the cerium and end with the lutetium. Next goes to 5f series elements. These are also called actinides. These are started from the thorium and end with the lawrencium. Okay, why these are called the lanthanides? Why 4f series of elements are called the lanthanides and why 5f series of elements are called the actinides? Because of 4f inner transition mates are known as lanthanides because they come immediately after lanthanum, and 5f inner transition elements are known as actinides because they come immediately after actinium. Because of the 4f series are called the lanthanides because of these are started after the lanthanum elements, and 5f series of elements are called the actinides because of these elements are started after actinium. So in each series 14 elements because of the f orbital is accommodate a maximum of how many electrons? 14 electrons, so that each series have 14 elements. Next go to rare earth elements. Rare earth elements. These are a set of 70 chemical elements. These are not extremely rare on Earth. They occur because they are spread very evenly over on Earth. So these are called rare earth elements. Rare earth elements are 4 series element and scandium and yttrium. These all are rare earth elements. And next goes to transuranic elements. Transuranic elements. What are the transuranic elements? After the greater than 92 atomic number, greater than 92 atomic number of elements are transuranic elements. Elements having more than 92 protons. That means elements have more than 92 protons are called transuranic elements. All of them are unstable and may of them disintegrate means decay quickly into other elements. This means they are all radioactive. Epoch elements. General electronic configuration is N-2F 1 to 14 and N-D 0 or 1 and NS2. Is 4F block elements, the electronic configuration here in these 4F block elements, you will take N is equal to 6, then you get 4F. Because of here N is equal to 6, you substitute in the place of N-2, then we will get 4F. 4F 1 to 14 and 5 is 0 or 1 and 6 is 2. This is the general electronic configuration of 4F block elements. These are the 4F block elements. These are called lanthanides. These are started from the cerium and with the lutetium. The cerium, praseodymium, neodymium, promethium, samarium, europium, gadolinium, and terbium, dysprosium, holmium, iridium, thulium, ytterbium, and lutetium. These 4 elements are 4F elements. Then atomic and ionic states of these lanthanides, atomic and ionic size. Atomic and ionic sizes generally in a period from the left to right, the ionic sizes are decreases with increasing atomic number because of the lost electrons are enters into same shell. In this lanthanide also, the study of decreasing the size of the atoms and ions of these four elements with increasing atomic number from lanthanum to lutetium is known as lanthanide contraction. Lanthanide contraction is nothing but study of decreasing in the size of the atoms and ions of four elements with increasing atomic number from lanthanum to lutetium is known as lanthanide contraction because of due to poor shielding effect. Because of due to poor shielding effect, and they are also with the different oxidation states, but the stable oxidation state of lanthanum is +3. In the case of lanthanum, gadolinium and lutetium, removal of 3 electrons is still 4f0 and 4f7 and 4f14 configuration. For example, gadolinium, its atomic number is 64. Its electronic configuration is xenon 47 5d1 6s2. Whenever it lost 3 electrons from the 5d1 6s2, then it gets the +3 oxidation state. In the +3 oxidation state, now it has F7. So it is the stable configuration because of half filled orbitals. Because whenever it lost whenever it lost 3 electrons from the 5d and says, then it gets the half filled d orbitals. The stable oxidation state of these lanthanides is +3, and they show +2 and +4 oxidation states also. They show +2 and +4 oxidation states in only F0, F7 and F14 orbitals of the elements. If they shows the +2 oxidation state of ion, it tries to convert into +3 oxidation state. Okay, if the ion has +2 oxidation state, then it try to convert into +3 oxidation state because of the stable oxidation state is element is +3. So it will undergo oxidation. So it is act as reducing agent. If ion in +4 oxidation state, then it is also try to convert into +3 oxidation state. So itself undergo reduction. Then it is act as oxidizing agent. The stable oxidation state is +3, but also they use the +2 and +4 oxidation states only F0, F7 and F14 orbitals. If it has +2 oxidation state, it try to convert into +3 oxidation states. So when it convert into +3 oxidation state, then itself undergoes to oxidation. That means it is act as reducing agent. If it shows the +4 oxidation state, then it is try to convert into same as usual +3 oxidation state. That means itself undergo reduction. That is, it cannot act as oxidizing agent. For example, cerium. If it lost 4 electrons from F5d and 6s2, then it has a F0. So in this cerium in +4 oxidation state, so try to convert into +3 oxidation state. Whenever try to convert into +3 oxidation state from the +4 oxidation state, then it is undergoes to reduction. That means it is oxidizing agent. So here cerium +4 ion is act as oxidizing agent. Same as well ytterbium. Then if it lost electron from the 6s orbital, then it's +2 oxidation state. Now it has a 4f14. Okay. Then in this, it's the
Thank you
+2
so much.
oxidation state.
Swapna,
So it's
Swapna madam,
converted into, sir.
conclude madam.
Okay, sir. So we will start next remaining.